97.5 for some odd reason. And some of you, I think it may have only been Chris, he dropped to a 50 because he didn't have his homework yesterday. But the rest of you only dropped to a 97.5, and I have no idea why you dropped to a 97.5. Even those of you who were absent yesterday and had no homework and had no lab grade, you still had a 97.5 average. So she sent us how to alter our preps today, which I have done. So everybody's average has shifted up and down tremendously from what it was yesterday. You no longer have a 100 average or 97.5. Now, I'm sorry, it's gone away. I do not know if it's correct yet. All right, Miss Glass is still out sick. She's having gallbladder surgery next Monday. She'll be here tomorrow, so I can go see her and check to make sure tests are counting the 50%, quizzes are 25%, homework is 10, and labs are 15. I don't know where to go in the PowerSchool to pull that up to make sure your grades are averaging at that percentage. All right, so until I can check to make sure your grades are calculating at that percent, I can't tell you with certainty that it's correct.
Do report cards for second quarter of the dog?
No, they have not gone out yet because Dr. Wells wanted us to recalculate first quarter grades, which may have altered final grades because of whatever glitch PowerSchool had that the state told us about. I can tell you personally from my grades, it affected one child's grade and a final semester average. It didn't alter anybody else's grade. There was some up and down movement in first quarter. There was some slight up and down movement in second quarter, but overall in final grades, it only moved one grade out of 65 students maybe. So it didn't do a lot for overall semester grades. So, but everybody had to go back through that process.
Do you have any idea when they'll listen out?
I honestly have no idea. I had heard February 5th, but I can't swear to that. Don't quote me on that. All right, so at number one, we're solving for what variable? Since you told me the equation, what's the variable we're solving for? Q, all right? So if we're solving for Q, it means we've got to know M, CP, and delta T, right?
Yes.
All right, so we're looking for M, CP, and delta T. So what's my M?
15.
All right, so 15.0. We got to know CP and delta T. So when I look back at the equation, or the question here, what's my delta T? That's usually the easiest thing for people to find. All right, see how it says we had an increase in temperature by 35? You don't have to subtract here because I'm flat out telling you the temperature went up by what?
35.
Went up by 35. So we're just going to write 35 for delta T. Now, my specific heat, because I didn't give you a specific heat, I didn't ask you to find the specific heat, you find it where? On your orange sheet. And the orange sheet tells you that we have what? Iron. So iron's specific heat is 0.449. So in order to find Q, we're going to do what? Multiply them all together, and what do you get? 0.72 is good. All right, so when we do this, we know the unit for Q turned out to be what? Joules. That was grams. That was joules over grams, degrees Celsius. That was degrees Celsius. So the Celsius cancels out, grams cancels out. We're left with joules. Now, when we go back to our question, we have how many significant digits there? How many here?
2.
So we want our answer to have how many?
2.
2. So we're going to round this to 240 joules. Now, if you rounded down to 230 joules, I would certainly not mark it wrong. Okay? 240 is a better answer. Questions? Would what? All right, number 2. So we're solving for what this time? Anytime they ask for identity, you need something off the orange chart. We've learned how to do this with density. What's the other thing on the orange chart? Specific heat. Okay, I heard a couple little weak voices out there. All right, but specific heat is what we would need to solve for. Okay? So, using our information that's given to us. All right. Q equals MCP delta T. So We're looking for CP. We got to have everything else. What do we know? The mass is 13.8, so I'll put that here. All right, what else do we know? Q is 856. All right, and I heard we know the delta T. Can somebody just tell me what it is? 60 what? You said 60.7?
Yeah.
All right, so to solve, you can do any number of things, but most people tend to do what? Most people tend to multiply and combine like terms. So 13.8 times 60.7, 837.66, and then times CP, and you get 856. All right, so to get CP, 837.66, 837.66. CP is going to equal 102. All right, so we don't need to worry about significant digits. We don't need to worry about units. What element do we have?
It's magnesium.
It's magnesium.
There's just spider on your board.
Where?
Just over there. What's crawling? It's somewhere over there. You should probably get out before it bites.
Okay.
I'm not sure.
I don't mind killing it. I don't mind doing anything with it, but I got to be able to see it.
Oh, it's going
So-
to have a fit if you killed it.
Live nowhere.
I really don't know. It was right there.
It was just right there.
It was a spider.
Look, people, I don't mind killing a spider, but next time you see it, tell me when it's out where I can kill it.
I don't want to interrupt you.
It's okay. I don't mind. I'd rather kill it than y'all get freaked out. All right, so the last question, what does specific heat tell us?
How fast is low heat?
Well, that's what I'd rather have, okay? The definition is really nice, but the definition is not going to serve you very well on the exam, okay? The exam is not going to ask you a bunch of crazy definitions, all right? So I'd rather you be able to tell me something like how fast or slow it cools, so, or how fast or slow it heats up, okay? So if something has a high specific heat, you know that it heats and cools how? It heats and cools slowly if it has a high specific heat, okay? Which is why, for example, hurricane season lasts into November. Water heats and cools very slowly. So once ocean water gets very warm, it takes a long time to cool down. So hurricane season lasts into November because it stays warm way into the fall. But does hurricane season start in, let's say, April or May when we're all running around in shorts and a t-shirt?
No.
No. Any of y'all go to the beach in spring break?
Yes.
Yeah, it's in April. How many of y'all get in the ocean and go swimming? Okay, we got one idiot in the room. Okay, I'm with Joyce. It's too cold. Okay.
Charlie Rice.
Okay. Still have an idiot.
So what are we right? So specific heat.
It tells you how fast something heats and cools. How quickly.
So anytime it says, what is the identity? It's always
And whatever the identity is, it's going to be an element. So what element was it? It was magnesium. Right? The identity will be an element.
Don't they think cooler than this?
No. Well, yes, if we get to the mini lab. If we don't get to the mini lab, no, there's nothing cool.
Let's go.
All right. So let's talk homework and see how we did. See what kind of issues we have.
I think that's kind of like
I'm not checking today. We're just going over. All right. So number one has three answers. So the first of the three answers should be negative 59 degrees Celsius. Okay.
I know how to go. I might be tricky, but I didn't know how to go Celsius to Celsius.
Same way. You still go. Okay. So So we'd say K equals 45 plus 273. And you would just add and get 318. Okay. That's what happens when you keep getting in the ocean in those cold temperatures. Okay? It's hurting your brain cells. Stop doing that. All right?
Drinking like 72 ounces of chill a day also.
Well, I gave up Pepsi, so I can't yell at you for that because I did it till I was 49. All right. Number 3 in that answer should be negative 423 degrees Celsius. No, technically there's an error in the question because you can't. What's back? Oh, I see. All right.
She doesn't want to break this.
There. All right. Number 2. See, now we don't have an issue. Number 2, you should have 81.2. All right. Now, round for significant digits. And you should get 80 joules over grams degrees Celsius. Yes, I will go back and work them. Okay, let me see what I've got. I told you to round for significant digits. I'll talk significant digits too.
Oh, okay.
Oh, yeah.
They're not recyclable.
Like the salad.
The first others were poppy seeds.
It's
It's
that.
been chicken, quinoa, kale.
Quinoa, that's what I meant.
But now I just did vegetables this
You like the
week.
superfood size from Chick-fil-A, don't you?
What?
Like the type too.
The what?
The superfood size, the kale and the dried nuts.
No, usually I get grilled
Grilled
chicken nuggets with ranch.
Let me get a side salad with ranch.
Yeah, no,
The
with
garlic
ranch.
herb ranch.
Too
Yeah, let's
fattening.
try the avocado lime.
I hate avocado.
All right, so number 3 should be 92.1 joules. Rounded to 90 for significant digits. 92.1 joules. It'll be 90. Moving on, folks. We're not moving very quickly. Number 4 should be 0.416 joules over grams degrees Celsius. Round to 0.4. Number 5, you get 10.7 joules. Round to 11. And number 6, you get 1,010.
Okay, I got it.
You only need 1 significant digit. No, 2 significant digits, sorry. And the only way you can do that one and get 2 significant digits is to put it in scientific notation. There's no other way to do that.
You gotta write 100 on it.
So you get 1.0 times 10 to the 3rd. Okay? Now, which ones do I need to do? All right, number 2. Ask you to find specific heat. Now, Q equals MCP delta T. So, when you look at the question, it says you have 4 grams. 4 grams is mass. It tells you go from 0 to 20 degrees. 0 to 20 degrees is what? That's 20, and that should change the temperature. It says you have 6,502 joules of heat. That is Q, and it wants you to find specific heat. So that's that. Yes, I know it's not the specific heat of iron. These are made up numbers. Clearly, they're not good numbers. So 2 times 20 is 80 times CP equals 6,502. Divide both sides by 80. And you'll find CP is equal to 81.2. Now, if you look at the original question, the 0 and the 20 only have 1 significant digit. So if you only have 1 significant digit, this has to be rounded to 80, which is why I rounded it to 80. Now, the unit is joules over grams degrees Celsius. And where's the shortcut I told you you could use to find that unit? On the orange sheet at the top of the column. All right, next one, Raquel. You got to have at least one number to write down or you don't have an answer. Well, you did. They have no decimal places, so you'd have no decimal places behind the answer. Remember, because you're adding?
So like on the second one and number one, it was 45 degrees.
Yes. So 45 has no places behind the decimal. So the 273 is a constant. You don't use it. So you have no places behind the decimal when you get done adding. Okay? You just don't have any decimal places. You use the least number of places behind the decimal when you add. Okay? And you only have that one number to use, so there's no places behind the decimal. So when you finish calculating, you want no places behind the decimal. Okay, you got me? Okay.
So anytime there'll be nothing behind, okay, so if we were doing this significant, then we were multiplying, if there's no thing behind the decimal place, then it just rounds up.
Well, when you're multiplying, it's about significant digits. So here, when we did this, all right, this is addition. Okay, this is about places behind the decimal. How many places are behind the decimal? None. So when you get that 318, you want no places behind the decimal. So that's why that answer is 318. We're not rounding that based on significant digits. We're not looking at the 45 and saying how many significant digits. Doesn't matter. We're looking at places behind the decimal. Decimals here, there are no places. Decimals here, there are no places. So we leave it at 318.
If you multiply it, you would round it off.
Now, then we would look and say, oh, there are two significant digits. We'd round that to 320. Because we're multiplying, it would be a different rule. Correct. Okay? See the difference?
So when you're doing Kelvin to Celsius or Celsius to Kelvin, it's not.
It's not multiplication, so it's all about places behind the decimal.
But when you're doing Fahrenheit, it is.
It's about multiplication. Correct.
Okay.
Correct. All right. What's next? Number 3. Now, Elijah, put your phone up. Number 3 is what? You said 3? All right. 3, calculate the heat. So if we're doing 3, which variable are we solving for? Solving for Q. It says calculate heat. So we're solving for Q. All right. What's my mass? 8.0. All right. What's my change in temperature?
34.
All right. 40 minus 10 is 30. And remember, you always use the positive difference, so there's no negative numbers. All right. And where do we get specific heat from? Yes, 0.384. They gave it to you in the question. All right, so now all you do is multiply them together, and you get 92.16. All right, and again, because we're multiplying, look at your significant digits in the question. You have 3 and 0.384, 2 and 8.0, but you only have 1 in 10 and in 40, so I only want 1 in this answer. So I'm going to round it to 90 in joules. I would ask why, again, like she said, but I would probably take it, but that's a really weird rounding. All right, next.
We must have sex.
Y'all must have been in the same class, I'm telling you. This is why I don't teach rounding. Yep. 4 says determine specific heat. So what variable are y'all solving for? All right. So what do we know in 4?
6.0.
6.0 is the mass. Q is 50. What's change in temperature? 20? 50 minus 30 is 20. So that's going to be 120 times CP equals 50. Divide 120. Divide 120. We get 0.4. 16 equals CP. All right. We can get our unit off of the orange chart. And then when we look back at the numbers we got that 20 from, they were 30 and 50. So because we had 30 and 50, That means we only had one significant digit, so we're going to round that to 0.4 joules over grams degree Celsius. What else? Anything?
We were looking for the significant, can you always divide? Because I can't, like.
You talking about the CP? Yes, you're always going to be dividing.
Do we have to put, after the answer of like 4 joules over gram Celsius, do we have to equal it in CP? Or you just put that in?
No, I just did. But you don't have to. I'm just used to because I used to teach math. What? Anything else? Are we good? Once upon a time in a former career.
Yeah, what kind of math was it?
Math 1, algebra 1.
Can you?
No. Just because I'm certified doesn't mean I ever will again. All right, so for homework last night, I asked you to see if you could come up with 2 more examples of things that were not matter. Okay. All right, I heard heat.
Is it?
Time will work.
I put smell. Energy, magnesium, gravity, smell.
We had gravity, I think, on the board. That works.
Energy.
I heard smell, energy,
Microwaves.
taste.
Magnetism. Yeah, magnetism. I didn't feel like writing that down. What's that? Oh, microwaves.
Microwave.
Now, when they say microwaves, they're not talking about the physical box that we microwave our popcorn in. They're talking about a type of energy that's called microwaves. Okay? All of those are fabulous. Okay? Now, notice no one said imagination or thoughts. Okay?
Imagination.
No, we're not writing that up there again. All right? Now, any of those are things that are not matter that you could have yelled out yesterday. Now, I also asked you to tell me the difference between mass and weight. Hold that thought. Okay? Does anybody need to write any of that down because you didn't bother to do that last night?
I'm just writing the one.
That's fine. Now, can I turn the board?
Yeah.
While I'm thinking about it, Dylan, who else was absent yesterday?
Oh, yeah.
Do you want the sheet we just went over? And I checked homework yesterday. Did either of you two have the homework from yesterday? There's a significant digit paper, 1 through 14. If you do, put it on my laptop up there so I can fix that in the grade book. Stick it there on the silver laptop, and I'll take care of that in college school. Because that one, put it on my laptop, that way you won't see it. Because I figured you probably had it, and I can take care of that later. All right. Now, somebody tell me what mass is.
The amount of material in the body that's measured.
Okay. No, I want you to tattoo it to your body. Yes.
I will.
What's weight?
What does that say? Gravity on an object.
The amount of matter in an object. I just shortened what Madison said because I'm lazy. Okay?
Weight exerted by gravity on an object.
Say it again.
Force exerted by gravity on an object.
Did everybody hear what she said? All right, say it loud enough they can hear you. They're deaf.
Force exerted by gravity on an object.
I've had a bad day, okay?
It's all. They just started.
It is.
Okay? All right, the force exerted by gravity on an object. Now, those are the definitions you should have learned somewhere in middle school. Somewhere. I don't know where. Some of you probably will tell me you had a sub. I don't care. All right, but you should have learned it somewhere. Now, the part that I want you to remember is the difference between the two. Because like I said, you are never going to be asked the definitions. Okay? In 45 questions on the exam, they're not going to ask you definitions. They're going to ask you application questions. So, what's the difference between the two? What? Mass stays the same.
And weight.
Weight changes with what? With location. Okay?
I really want to weigh what I'm weighing to move.
Me too. Jupiter is not a place I'm ever going.
Oh, yeah.
Okay? Mass stays the same and weight changes with location. Now, we just said that several of us would love to go to the moon, and I said I would not want to go to Jupiter. Is everybody with us on why?
Yes.
Okay? Why would I be okay with going to the moon? Gravity is less, so I would what? I would weigh less. Why am I not okay with going to Jupiter? It's a bigger planet, so it has what? More gravity, I would weigh much more. Okay? Never going there. I don't care if they ever make it workable. All right. We're going to talk about physical properties and chemical properties first today. And then we're going to work our way into changes. And if all goes well, we'll get to start the mini lab today, which is the plan.
Yeah, okay, I started the shift.
Yes, you did. Yeah. Now, a physical property is a property that can be observed without altering the identity of a material. Yeah, we know the song. Even I'm not so old, I don't know. Now, I want you to look at my desk that's up front. Pretend there are not notebooks sitting on top of it.
But they're notebooks or they're not?
Big round.
Oh.
Not the round desk. The big rectangular. All right, and I want you to give me some properties to describe the desk. I do not want you to tell me there's crap sitting on it. Okay? It's what? Okay. So, what would you tell me about it's wooden? It's
Hardwood.
It's hardwood. So hardness. Hardness would be a property. Brown is colored. That's a property. It's a solid. That's a property. Texture is a property.
So these are examples.
It's dough.
Yes.
Wait, so at least it's
Yes.
It's cold.
All right. Temperature. So what kind of temperature could we give about it that we would specifically use this semester? What kind of temperatures do you think we might use this semester instead of just referring generically to warm or cold?
Freaking cold.
No.
Very high.
I'll give you a hint. You got your orange sheets handy?
Yes.
Look at that. There we go.
How do you boil?
Melting point.
Oh,
it's right here. Right.
Now, we can't refer to something as being cold because some people would tell you today is overly cold or this room compared to another room might be considered warmer or colder than something else. If I gave you 2 containers of water and I had you put your hand in one of them and then the other one, and I gave you 2 more buckets of water at a different temperature, you would say that one is cold versus the other one might be warmer. What?
We had to do that in Bowers class.
Yeah. So it's very difficult to compare something as being cold. Cold and warm are relative terms depending on another temperature. All right. But melting point and boiling point are not relative. That's a particular temperature. All right. Give me something else.
That isn't it.
Give me something we've learned to measure that we could describe about the desk.
Inches.
All right. Length. We could measure it in inches, but we're not measuring anything in inches. Volume.
Density.
Sure.
Mass.
Sure.
Okay, there you go.
Instead of saying joules, joules would be what?
Grams.
No.
Specific heat.
Oh, tobacco.
Give me one more to fill up this space.
Are you kidding me?
No.
They equal mine, so I'm not writing it. Yeah, they equal.
So we have 4, 4, and 4, so we're not writing it. Okay. So, physical properties. Let me say this. Only physical properties can be labeled this way. Okay?
What do you mean labeled this way?
Extensive and intensive. So in a minute, when I talk about chemical properties, are we going to go back and label them as intensive and extensive? If only physical properties can be labeled this way, are we going to go back and label chemical properties as intensive and extensive?
No.
No.
Which one's first? Extensive.
It doesn't matter. I wrote extensive first, but it doesn't matter which one you do. Extensive are properties that depend on size or amount. Intensive do not depend on size or amount. Let's go with that color. All right, so we want to go back to the properties we just listed, and we want to figure out which ones are intensive and which ones are extensive.
Color is intensive.
Okay? Everybody caught up?
No.
Okay. So if I take, for example, Cecilia's black JROTC jacket over there, and I cut it in half. And I throw one half on this side of the room, and one half on that side of the room. Is the color going to change? No. So that would be what? Intensive. Color is an intensive physical property. It doesn't matter the size or the amount. If I cut it into fourths, and I give a piece to Miss Bowers, a piece to Miss Rector, we keep a piece, and I give a piece to Miss Wicker. Is the color going to change?
No.
No. Everybody caught up now? All right, so color is intensive. Size does not matter. So, for mass, if I cut my desk in half, we keep half, and I drag half of it over there to Miss Bowers. Is it intensive or extensive? It's extensive. Mass depends on size or amount. Okay? So, the remaining 10 up here. Which ones are they? Hardness is intensive. No. It's what? It's intensive. Think about your lab yesterday. Not yesterday, the day before. That's why you got the wood question wrong. The density of the wood didn't change. Okay. Length of the desk is intensive. If I chop it in half and take Ms. Bowers half of it, the length did not change. Length is what? It's extensive. Where's length at? Right there. The volume is what? The volume is extensive. Melting point is intensive. And what?
Melting and boiling.
Now, let me give you a hint. See that orange chart?
Yeah.
Everything that's on that orange chart is what? Intensive. So what else can we label intensive? Correct. Because if they can give you the number and label it on that chart, is it going to change? No. The specific heat of iron is 0.449. Every time you need it, you look it up on that orange chart. It is not going to change regardless of the size or the amount. Dullness is intensive. Okay? All right, solid. Texture. All right, most people get a few more E's up here for me, but y'all didn't. It's all
How
good.
many E's is length, volume, and mass?
That you guys named. There's a lot more you could have named.
That's all we're naming. It'll be with my list.
Okay, I've got no issues with that. All right, so chemical properties. Yeah. Chemical properties are properties that will alter the identity of a material. Okay? Things that you might choose to put here would be flammability.
Examples?
Yes. All right. No, I was going to put a few more if it was all right with you. I was just giving y'all a chance to catch up since you're usually telling me I'm going too fast. All right. All right. How about reactivity? How about the ability to decay or decompose? Do one more. The ability to oxidize. Most people in chemistry know what that one is already. What's that one? Yep. Rust.
Can I put rust or not?
Doesn't matter to me.
There's one that says another idity.
There's another idity.
Yeah. Like flammability. I watched on build out, but I can't think what it is. Oh.
Let's see. All right. Everybody good?
No.
Catch up now. All right. It's going to take about 3 minutes. This side of the room probably haven't done before that side. You have to pay. You done?
Yeah.
And you have to work on that. I'll make it faster. This is supposed to have a backside to it, but I messed it up on the copier, so you get 2 sheets of paper today. And hopefully I have enough copies, because, you know, Taylor joined us, and I might have to come make a copy real quick.
How many people are in this class now?
29.
We have a lot of people. This is the biggest class.
Ooh.
It doesn't look as big.
It's because the room's really big. All right, this is easy. Put a check mark under or beside each thing based on whether you think it's physical or chemical.
I do text you. That's not what I was trying to do.
Remember, as soon as I put in these 3 homework grades.
It was solubility, that's what I was thinking of.
It was what? Solubility?
Yeah.
Luster or shininess?
Oh.
Are you serious?
Anybody have any questions?
I'm not saying like, I'm not saying like,
All right, we'll go over it.
Yeah.
All right, since I gave all my copies away except Faith's, I gotta find it. Normally I have extras, so I don't have to stare over somebody's poor shoulder. All right, number 1. What'd you put for color? Density, flammability, solubility,
physical.
physical. Being able to dissolve is a physical property. Reacts with acid to form hydrogen. Chemical. Supports combustion. That's chemical. Sour taste. That's physical. Some things just taste sour. All right. Melting point. That's physical. Reacts with water to form a gas. Reacts with the base to form water. Hardness. Boiling point. Can neutralize a base. Luster. That's physical. That's shininess, if anybody didn't hear me answer that a while ago. And odor. Odor is physical. Some things just smell bad. Yes.
For 3, for 3 is chemical, and then 4 is physical.
That is correct.
Oh.
All right. Everybody got it? All right. So the second half of the lab that you're going to do is on physical and chemical properties. Sorry, physical and chemical change. We just did properties. Change. Now, physical change. Now, we can use the same definition for chemical change in that, all right, the material will not be altered. However, what about it will not be altered? You will not get a new material. The thing that I want to clarify here is you might get a different state. Now, most students get hung up on physical change. Physical change will make more sense to most of you after we do chemical change, because I'm going to give you 5 things to look for. If you don't see any of these 5 things, then it's automatically a physical change. Okay? So, most of you, if you did this in middle school, which again, you should have, all right, most of our first unit is largely review. I just do it because a lot of you did not have most of these experiences at some point.
Or we don't remember.
Or you don't remember it. I know. Are you the crowd who told me you were middle schoolers and had hormones running around and you don't remember any of this? I thought it was Joyce who told me that. I thought so. All right. If you tear something in half,
I thought it was tears.
Physical.
all right, maybe, but I thought it was spelled right. All right. If you tear something in half, if you grind something up, all right, if you shred something, chop, all of those types of words that you would use, those are all going to be physical changes. Where students get in trouble with physical changes is when we start talking about state changes. Okay? When we go to things like water, yes. Okay? Because they automatically go to, oh, no, not chop. We don't chop water. We chop. Oh, yeah, that's chop. So, like, if you, for example, last night I used onions in dinner. All right? If we chop the onion up, everybody can agree it's still a what when I got done? It's still an onion. The onion has not changed form in any way. It's still an onion. Most of us can agree after I cooked it last night, it still looked like an onion, still tasted like an onion. I've not altered the onion in any way. It's still going to be a physical change. Okay? Now, state changes, however, can anybody give me a state change? From gas to what? Liquid. What's a gas to a liquid called? Condensation. Okay? So, now, we teach the water cycle at middle school like nobody's business. All right? Gas to a liquid is condensation. Evaporation is a liquid to a gas, in case you forgot. All right, melting is a solid to a liquid. The opposite is freezing.
No.
That's a liquid to a solid. And I'm going to put sublimation up here. We'll save the opposite of it to later in the semester when we get to it. Is a solid to a gas. Now, anytime you have a state change, state changes are always physical changes. You still have water if you're talking about water freezing or water melting. Nothing happened to the water except it changed its state. Okay? So it's still water. Now, when we go to solubility, that was on our paper a second ago. Let's take sugar. All right? Everybody in here has made Kool-Aid at some point in their lives, even if you don't like Kool-Aid. All right? Or sweet tea. All right? Sweet tea is the nastiest thing on the planet. It's nasty.
I drink tea.
I don't like the taste of any kind of tea. Green tea, sweet tea, hot tea, warm tea, cold tea. Nasty. Now, my point is, sugar has what type of taste to everybody in here? How would you describe it? That's the word everybody would associate with it. Now, if you put it in water, well, how does the water taste after you do it? Exactly. So, the sugar did not change at all. Okay? So, when you dissolve something, dissolving is still a physical change. Okay? Nothing happened to it. All right? It just dissolved in the water. The sugar still got the same properties. It's still sweet. Okay? What? The only one that I can think of that would not be a physical change is something like Alka-Seltzer. And you'll see why when we talk about the 5 indicators of chemical change, because it produces a gas.
Wait, so
Okay.
dissolving is a physical?
What? Dissolving is, all this stuff is physical changes.
So what does it fall under? Is it extensive?
Those are properties. Intensive and extensive are physical properties. We're talking about change. Okay? Now, how can we tell if something is a chemical change, since y'all are dying to know? Now, in a chemical change, we already said that we alter the identity, right? And I'm just going to write ID instead of identity. Now, With a chemical change, you get a new material with all new properties. Now, to illustrate this, I'm going to give you an example that most of you know what the compound is.
Like water. Never mind.
Salt.
Carbon dioxide.
Salt.
Salt. All right, what can you tell me about NaCl? How would you describe it? Okay, give me something else.
Sodium chloride.
What color is it?
White, right?
Okay, what state is it?
Solid.
Okay, it's a powder. I'm going to say it's granular or crystal. And I'm going to write that it's safe to eat.
Is that a plus NaCl or equals
Where? Here? It's a plus, and that's an arrow.
arrow?
I wrote it as a balanced equation because we're going to learn how to do that. Now, NaCl, everybody's familiar with. It's white, it's a crystal, and it's safe to eat. Now, I'm not telling you can eat a salt shaker every day for 25 years and not have health issues, but you can sprinkle salt on lunch today, and you're not going to drop dead in the cafeteria.
You could. I wish I could.
Let's hope not. Now, I say this because sodium is a silver metal that explodes in water. The vast majority of our saliva is water. So if we put a sliver of sodium metal on our tongue, we're done. Okay? Our head would explode.
So this is sodium. Na is sodium.
Na is sodium. Chlorine is a yellow, poisonous gas. Breathe a little and drop dead. Okay? Both of those chemicals that make salt are highly toxic. We can't be around them. I can't have either of those two in the science building. Sodium, if you go to a college that has them, a lot of professors in a first-year course will demonstrate sodium in the top of the beaker spinning around a very small amount so that you can see it bouncing around, creating a little spark and flame, a small explosion on the top of the beaker. It will be an incredibly small piece so that you can see it. Now, chlorine, none of us will have. All right, it's deadly. Put the two together, and it explodes and makes salt. Not the way we make salt, by the way. All right? Now, my point in this is, if you undergo chemical change, you get a new material, and it has all new properties. Does NaCl keep any of the original properties?
No.
No. In a physical change, do you get all new properties after you undergo a physical change? No, you keep the same properties you had. Sugar, when you dissolve it in water, still has the same properties you started with. It's just dissolved in the water. Okay? If you wanted the sugar back out of the water, what would we do to get the sugar back out of the water? Anybody know? Evaporate the water, and you can get it back. Okay? It's not gone. If I have this, can I get the chlorine gas back? No. Okay? Now, how can I tell if I have chemical change? We never do that. Everybody hear me say we never do that? We never taste stuff. If that's ever an answer on a test, please, dear Lord, don't pick it. Never, ever, ever do that. Now, the first indicator of chemical change is the production of light. So the equation that I just showed you for making salt, when you put sodium and chlorine together, it makes a huge explosion that produces light. Hence the reason we don't make commercial salt that way. Number two, I already told you the second one. If you were listening, I told you the only physical change I could think of that would, by dissolving, that is not actually a physical change was Alka-Seltzer. All right, when you put Alka-Seltzer in the water, what happens? It bubbles and makes a gas. The production of a gas, and you would be looking for bubbles in the lab, all right, is going to be the indicator of a chemical change. Number three, color change. Now, let me preface this by saying it has to be unexpected color change. Now, if you go to the store and you buy grape Kool-Aid, and you go home and you make grape Kool-Aid and it turns purple.
Whoa.
That is not a chemical change. That is purple food dye. It turned purple. Okay? Now, if you take a clear liquid and a clear liquid and it turns purple, that is an unexpected color change. That is an indication of chemical change.
So do we only need one?
You only need one of the five. Okay? But you have to have one. Yes.
Isn't that like in the Bartholomew glue or whatever? I forgot the name of it. You blow into it and it turns green.
Yes, that would be a chemical change because it's unexpected. Okay? We use lots of indicators like that. If any of you did you ever use lime water?
No.
No. Okay. I don't have that one. I'll talk about it in a minute, but I don't actually have that one. Okay? Now, a lot of times people ask me about the leaves changing. People get this one wrong because leaves changing. Are leaves changing expected or unexpected? Expected. That's the answer I get all the time because y'all see it happen every year. Okay, leaves are what color?
Green.
Green. When they turn red and brown and yellow, technically it's an unexpected color change. Okay, that's that whole biology process y'all learned about. So it's an unexpected color change. Okay, that's a chemical change that happens inside the leaves. Okay, so that one would be a chemical change. Okay, y'all learned about it last year.
Yeah.
Chlorophyll, all that good stuff. Don't ask me about it.
You know, I don't even know. I've been here for a long time.
All right, number 4. Change in temperature.
Anytime or would it be rapid?
Now, there are 2 temperature changes you should have learned about somewhere in another science class. One is called endothermic
Oh boy. Yeah.
and exothermic. Not sure which one we can pin that one on, but you should have learned it before me. All right, endothermic means heat is, okay, we got the inside part, so heat is absorbed. All right, exo means heat is released. Now, you're going to have to know about it in terms of how it feels. So, endothermic is going to feel cold to the touch. And exothermic is going to feel warm to the touch. Now, I say this because you're going to need to touch the baggie and the test tube in the lab. If you don't touch the baggie and the test tube, will you be able to tell if it's endo or exothermic? No. Okay, you and your lab partner will have to touch things. And I have enough baskets set up for us to have lab groups of 2, and there's 28 of us here today. So we'll have lab groups of 2. Okay? Now, the last one is a new vocabulary word for us today. All right? the formation of a precipitate. That's why I said it was a new vocabulary word. A precipitate is not rain in chemistry class. We use science words interchangeably all the time and give them new definitions. Why we do this, I have no idea. All right, in chemistry class, a precipitate is a solid formed from two liquids. I will improve on this definition later in the semester, but we are not sophisticated enough for a more advanced definition, so this will do for right now. It's a solid formed from two liquids.
Like cheese, like he said.
Like what?
Cheese.
No, I mean like two liquids, not cheese.
But cheese turns into liquid.
Liquids.
You melt
You
it,
can make that
water.
an elephant toothpaste, something like that.
No, I mean like they're two, literally like two things of water. You mix two things of water, it turns into a solid. No, I don't mean cheese.
I know, it's like making slime.
What's
It's like making elephant toothpaste. Oh yeah, it's like slime.
We should make some.
No, I've made enough slime in my lifetime.
While those are shirts that they are the bowl is green. And it's
Oh,
going
what's
in,
that?
yes, it's all coming on.
What do bees? Oh my god.
All right. On this particular sheet, aside from telling me if it's physical or chemical, I want you to tell me if it's chemical, what the indicator is. Okay?
Wait.
So, if we do the first two together. And number one, thank you. And number one, sodium hydroxide dissolves in water as what? Right, physical, right, P, I don't care. All right, number two, hydrochloric acid reacts with potassium hydroxide to produce salt, water, and heat. Okay, what's the indicator since you said chemical?
Yeah.
All right, the indicator, so if you have the right answer before I yell. All right, has to be one of these five. Light, gas, color change, temperature change, or precipitate. All right, so which one would the heat be? Be the change of temperature. You can just write temperature.
So that's
Okay.
only for chemicals, not for physical.
That's only for chemical, not for physical. Correct. Okay?
When are we gonna try to do the lab?
I think we'll have time to get started on it. I don't think we'll be able to finish it. What I'm waiting on. Let those people finish. Who's still working and needs to be awake? We good? All right, number one. The two we did, so we're on number three. What do you think? All right, that's physical. Sliced is physical. Number four, heated and changed to steam is physical. Number five, decomposes to form potassium chloride and oxygen gas. Chemical, what's the indicator? Production of a gas. Number six, iron rust. Chemical, what's the indicator? Color change. Anytime you rust, I'm sure somebody's seen rust in here, changes color. When placed in water, a sodium pellet catches on fire, produces hydrogen gas, and forms sodium hydroxide. Chemical, what's the indicator? Gas and production of light. You could even give me one more. Temperature. Any of those three are fine. Evaporation. Physical. Ice melting. Physical. Milk sours. It's actually chemical. Any ideas which one? It actually does form a precipitate. If you've never seen milk souring, you have to go far enough to see that. Most people don't.
It gets chunky.
It gets chunky, which is pretty gross. It curdles. It's nasty. It smells really bad too. You've never let it go that long. I don't recommend it. All right. Yeah. You'd have to leave it long enough for that to happen. Most people never get that far. Sugar dissolves in water. Physical. Wood rotting.
Chemical.
That's chemical. Any ideas which one? It will produce a gas.
It changes the.
It does change the color. And there's one more. You notice it more in the winter than any other time. Temperature. It produces heat. All right. This one, if you've never done it, you probably don't know the answer to this. Pancakes cooking on a grill. It is chemical. Any ideas why? The bubbles. It produces a gas. That's why I said if you've never done it, you wouldn't know the answer. All right. Now, before you yell this out, your biology teachers are going to be crushed if you get it wrong.
I'm scared.
All right. And I will rat you out.
Pass.
All right. Grass growing in lawn.
Physical.
All right. So we got a half and half of the room. All right. It's a plant. Does that help any?
Yes.
Chemical.
It's chemical. What process did y'all learn about? Photosynthesis.
You know?
Right.
All right. So it's chemical.
So what's the
What do plants take in? Yes, they take in oxygen, they make carbon dioxide. You could have told me about light. Could have told me about light or gas. All right. A tire is inflated with air. Physical. Food is digested in the stomach.
Chemical.
Yes. Why? Gas.
Temperature.
Temperature. My favorite when you left off. Color change. I'd almost guarantee that food didn't go in the same color as it came out. All right. Water is absorbed by paper towel. Physical. With the exception of corn.
Are we done with those?
Yep.
Hey.
All right. I need 3 volunteers who can keep track of who's up and handing out papers. And give one to everybody that's out of their chairs. All right. Don't forget each other. Need one more. Linda's been really good. Give her a break. Everybody. All right. So you 3 make sure everybody here gets one and everybody else in the room. Now, the 2 papers that Cecilia and Karen are handing out are homework. / the 2 that I have not handed out for test review. Now, the one that says conversion and density practice, I strongly recommend you take a little time to do tonight because some of you are going to get stuck on that simply because, got a little challenge in it to go with some of the questions on the test. So some of you are going to think I lost my mind tonight when you look at some of those. You'll find some bolded units that don't match to solve the problems. So take a look at that. The other one's sort of fluffy because it went with what we were doing today, and that one should be pretty easy and not take a lot of time. The other one is your lab sheet that Madison's hanging out. So what? Yes. You go about something else. Why doesn't she tell me these things?
She doesn't really care. Yeah.
This is like last semester when they let me call that boy Lewis and his name was Luis for an entire quarter. He's probably why I stopped coming to school.
Louis Sue.
Oh.
Cruz Mason.
Oh.
Boy never came.
Oh.
He was 66 days. The only day he showed up in my class was the day of the lockdown that code yellow. When we couldn't leave to go to second period, and he showed up late for second period, and they brought him to class. He was stunned when he had to come to first period. He didn't even know what to do. He was so shocked.
So we're gonna get started on the lab. And then this is
Now, yeah, test is Monday. Now, the test is Monday, even though I handed you the 2 test review sheets that I had left over. All right, the test will be on Monday. It will not be tomorrow. Now, hello, Colonel. Let me get them started on what they're going to do for lab, and then I'll show you what we're going to do for fourth. All right, the lab sheet is obviously the one so lab. Just in case any of you were confused. Now, we're only going to do part 1, okay? The part that says part 2, it says demo, we'll do that tomorrow. So we should be able, I think, to fill out the part 1 section. If you finish part 1, I need you to throttle back and work on your homework before the bell rings, okay? Now, in each basket, you will find, the baskets are here, try not to run over each other and knock my desk over while you're getting them. The baskets are here, and I'm not even going to show you how to use part 2. The baggies, the bottles, the test tubes, you don't need any of that today. You'll need the rulers, styrofoam, you'll need to get a scale out. The ones on the bottom 2 shelves will work, the ones on the top shelf will not, leave them big. Notice how they're in the cabinet so that they're put back the same way they're in there. Don't put it in backwards, it drives my OCD crazy. All right, I know the styrofoam looks a little rough. It's okay. You're not looking for accuracy on this. You're just going for general answers, okay? In the column that says observation or measurement, don't write observation or measurement. In the first one where it says volume, find the volume of the styrofoam block to the correct significant digits. Then tell me if it's a physical or chemical property and label it intense or extense. Do that for the entire data table in there. Each of these has enough for 2 groups. So if you come to get a basket, let's say for this counter here, if you're already that counter with a basket, make sure you check that table already has a basket. There should not be 2 baskets at that counter. So there's 7 baskets, 1 for all 6 counters and for the movable lab counter over there. Everybody got it? So 1 for each counter and the movable one. And because you're only using styrofoam today, we don't need the eyewear and the aprons until Monday.
Dang it.
Okay? Fabulous. Get started. You got 15 minutes to do part 1, and then you can work on your homework. How are you today? Good to see you. Good to see you. Hold on. Okay. Let me get rid of what I have them doing and pull up what you're going to be doing.